All right, so today we're starting chapter 32. We just finished chapter 30, and we're going back to chapter 31 afterwards. Chapter 31 talks about essentially electromagnetic waves. We're going to kind of touch on that. We're not going to go, when we do talk about chapter 31, we're not going to go into every detail that it offers. But we're going to talk about chapter 32 first, which is AC circuits. Go through that, and then we'll come back and get chapter 31. So chapter 32. Chapter 32 is going to talk about well, kind of how we ended our class last time. So last time we had let me see here. We can draw this out. Do something like this. Okay, so let's say we have these two magnets here. Okay, and in these two magnets, you have a magnetic field that's being created. Let's say it this way. And we put a loop of wire in it. Okay, and it's connected here to the circuit. So I have to put a resistor there. Okay, and then this thing rotates. Right. So last time when we talked about Faraday's law, we saw that when you do that, you're going to get a flux here, and that flux is going to be changing. And as that flux changes, according to Faraday's law, we get a sinusoidal function. So I'm going to write this function as E max cosine omega t. Okay. Now, I think last time, if you look back at your notes, we had sine there. It doesn't really matter if you use sine or cosine. That just changes your initial position, right? So if you do sine, then your initial voltage is 0. If you do cosine, then your initial voltage is at maximum. So we'll just stick with cosine. And so as a function of time, this is going to look like this. Right, something like that, where this value here is E max. Okay, and you get that sinusoidal function. And remember omega here, just as a reminder, omega is related to the frequency. So omega is 2 pi f. All right, 2 pi times your frequency. Okay, so we have this alternating here, and it's going to alternate so that so if our frequency is f, that means we could get the period here. So as it goes up, it goes down here and then goes back up. Right at this point, the cycle repeats and it's going to go down and then back up. So remember when the time it takes for the cycle to repeat, it has a special name here. Call that the period. And that period is related to the frequency, right? In 1 over frequency. All right, so if you remember what frequency is how many cycles occur per second, whereas the period is how many seconds it takes for the cycle to complete, right? So it's just inverse of each other. T is in terms of seconds here, so that would be in seconds, and F, that's in terms of hertz, right, or 1 over seconds. Okay, so that's what we're looking at in chapter 32, just this alternating voltage, which we call AC. AC stands for alternating current. And you can see that voltage is positive, and then voltage becomes negative. So what that means is that the polarity here, at one point you have maybe something like this. You have a positive and a negative, and then let's say that's at E max here, positive E max, and then it's going to flip polarity. And then at another moment, it's going to be something like this, negative and positive. And you keep having that flip. It keeps changing polarity, and it keeps changing polarity, then current is changing. All right, so let's talk about current. If we have a resistor here, R, we know Ohm's law still applies here. The resistor here is feeling the voltage coming from your power supply here. In this case, your coil. Eventually, I'm going to take out this coil and just put a symbol. So actually, let me just do that now. So instead of drawing that coil magnetic field, we could just write an AC circuit like this. Yeah, the omega is 2 pi f. Okay, so this is something similar to that. The little symbol there on the left with a kind of squiggly, almost like a sine curve, that represents a AC power supply. Okay, so we have an AC power supply applied to this resistor, and now Rebecca, now that you said that, I want to change it, just to make sure that it's clear for everybody. That's a little bit better, right? Okay, so we know that resistor is still going to follow Ohm's law. So Ohm's law, if let's say we're trying to find current here. Let me do this in blue. Ohm's law equals voltage over resistance. So what voltage are we looking at? Well, we're looking at the voltage from the power supply. So this is going to be E max or V max, whatever you want to use, cosine omega t divided by R. Okay, so we have E max cosine omega t over R, and E max over R. Well, E max over R that's just voltage over resistance. That's just going to give us I max cosine omega t. Okay, so and same omega, right? Same frequency and same function, cosine. So the cosine curve we're going to draw in the same graph. It looks really similar to that. It looks something like this. Okay, so it's kind of following. It's following that voltage there. As a voltage reaches its positive max, current reaches its positive maximum. As the voltage reaches its as you get zero voltage, you get zero current. All right, and that shouldn't be surprising. This is something we've seen ever since chapter 27, I think. That voltage and current are closely related, right? Voltage increases, we know current's going to increase. So when we look at this graph up here, we say that because they're kind of increasing at the same time, decreasing, reaching zero at the same time, we say that current and voltage are in phase. Okay, I could put it here. So they're in phase with each other. Now, like I said, that's not super surprising. We're going to see the same. Let me say this: we're not going to see the same thing when we put a capacitor in there or when we put an inductor in there. Right? We're going to see very different things. They're not going to be in phase. But for the resistor, being an ohmic device, just follows Ohm's law. So, pretty straightforward relationship there. Okay, so let's say I have, okay, well, on this slide, we're going to talk about this. We're going to talk about something called phasors. Okay, so let me draw my graph again. Do it black. So the voltage looked like this. And the current was very similar. So the blue is my current, I, and the black is my voltage, called V. Okay, so what we're gonna do is represent this in terms of a vector that that goes around. So let me draw it. Let me draw an x-axis here and a y-axis. Okay, and I'm going to have my voltage be a vector. Okay, this is my V max here. Okay, now if I want the x component, right, of this, I need to know this data. And so the x component, we can call this Vx. V max times cosine theta. Okay, now this is where it gets a little tricky. This voltage, this vector here, voltage is not a vector, but this is why it's not called a vector. This is why it's called phasors. Okay, so this phasor here isn't staying stationary. What this phasor is going to do is move around like this. Okay, it's kind of going at a circle. The magnitude is staying the same, right? I'm trying to do my best to keep it the same. The magnitude is staying the same, but we're going around in a circle here. So let me go back and put it back where it was. Okay, so if it's going in a circle, that means that theta is not staying constant. In fact, we learned a little while ago that, and I think we talked about it last class, that theta, if it's not constant, we could represent theta in terms of its angular speed or its angular frequency, right, omega t. So my equation for Vx is Vmax cosine omega t. That looks familiar, right? We just saw that. This equation right here is the same equation, right? Vmax cosine omega t as we saw over here. So what's that telling us? That tells us that the x component of this phasor, corresponds to the instantaneous voltage. Okay, so in other words, the voltage that when we look at the x component, that's telling us what voltage is going through that circuit at that time. Okay, so let me look at a couple examples here. Let me erase this because I'm going to draw on this now. Okay, so I'm going to look at a couple examples. Let's look at this example. Let's look at my initial time. Okay, how does my phasor look like initially? Well, my initial phasor is going to look something like this. Okay, so it has a magnitude of V max. And if I'm at maximum here, if I have a maximum value right here, right, my voltage is at maximum, then the x component has to be at maximum. All right, if I look at a different position, I don't know how many, we'll see how many colors I could come up with. Let's look at another position here. Well, my voltage there is 0. And also we have to note that voltage there is not only 0, but it's going from a positive voltage to a negative, right? As we're going down this way, goes positive voltage, goes to 0, and then becomes negative. Well, remember, on my phasor, I'm going to represent that same behavior with my x component. So when is my x component 0? We have a 0 x component when your voltage is like this. And again, the magnitude here still be max. I'm not changing the magnitude. Okay, so I'm not changing my magnitude there. Let's pick one more position. Let me do I think if I pick this position here, I think you would know, right? This is a negative x component. Let me just do it. So when do I have a negative maximum for my x component? And that's going to be here. Okay, so what we're looking at there is that phasor at different points, at different times. That phasor is going in that counterclockwise direction, and as it goes around that direction, and we just focus on the x component, is letting us know what is my voltage at a certain time. Okay, so I'll keep that phasor up there. Let me draw another phasor. Right, so like I said, we have a voltage. Right, this is our V max. And the whole point of this V max is if you look at the x component, it tells you what the instantaneous voltage is. So again, I'm going to draw it one more time because I think it's helpful to visualize it. Oops. I was able to do it last time. There you go. Okay, so that V max, or that voltage, is going around in that circle. And I'm just stopping at different times, right? When I have maximum voltage, positive maximum, I have here. When I have zero voltage, right, it's here. And that's going from positive to negative, right? So so that's at zero voltage. And then negative maximum voltage, and then zero voltage again, right? Because if you look at the x component, when the vector's down here, I know that the arrow's getting a little distorted there. When I have my vector pointing down, right, it doesn't have an x component. And this vector is going from a negative x component to a positive x component. I don't know if you guys can see the little arrows. If you look at the arrows, not the arrows, the dashed lines of like this. I don't know if you guys can see this box that this vector makes as I move it. But you can see that it's going to have the negative x component, and then goes to zero, and then positive x component, right? And so it keeps going around. Okay, so that's what we're looking at when it comes to phasors. Now, the reason why this is helpful, well, it'll become more evident later. When we talk about current, though, current is in phase with the current, with the voltage. So I'm going to have another phasor representing the current. So there's my current, I. And we said voltage and current were in phase, right? That's what we said last time in the previous slide. Okay, so that means as voltage is going around in a circle, I can't twist both of them, unfortunately. As current is going around in a circle, well, maybe, okay, I can't. Everything moves. Oh, never mind. All right, so as voltage goes around in that circle, current is going to be right on top of it, right? Matching the frequency. When voltage has a 0x component, current is going to have a 0x component. So I hope that as far as why we need them, we will be talking about that, especially when we get to capacitors and inductors. If I put a capacitor and inductor in an AC circuit, like I said before, it's not going to have the same behavior. So these phasors are going to be particularly helpful when it comes to that. Okay. So one more topic that I want to talk about today, and that is power in AC circuits. Okay, so power in an AC circuit. Well, remember what power is. When we talked about power going through a resistor, here's the equation we had. Now, when we talk about, in our case, our current is not staying constant. In fact, we have a function for current. We're still talking about the circuit with a resistor, right? So we saw that current is going to be I max cosine omega t, and all that is going to be squared and times r. All right, so that's my function for I that I had, what was that, a couple slides ago? Let's go there. Right here. All right, we use Ohm's law, and we got this function for I. Okay, so I is fluctuating, right, as a cosine curve. So when I'm talking about power, well, I still have that fluctuation. Okay, and so we're going to plug that in. Or let me simplify it. So get I max squared times r cosine squared omega t. So how does that look? That power, if I were to plot this power as a function of time, cosine squared looks something like this. I'm not doing a good job drawing it, but okay, something like that. Okay, so power is this is a function of time here. So power is fluctuating. So when we're looking at this, it's not super helpful here to say what's your instantaneous power, because remember what power is how much energy is delivered per second. Well, that's constantly changing, right, according to that graph. So we're going to look at average power. So let's try to find average power. Average power. Okay, so when we're back in calculus, we could find the average of any function with this equation here. So your average of some function is equal to b minus a, and the integral of a to b fx dx. All right, so that would be your, let's say average here. So messy. There you go. So you average some function over the interval b to a or a to b is given to us according to this. So we want to take the average over a period, right? Because once you take the average over the period, the cycle just repeats itself. So if we're going to look over let me write that in here. So we're going to calculate the period, or the average power over one period. Okay, so in our case, we're going to say P, whoops, P average equals, and the limits here is going to be from t and 0, from 0 to t. So we're going to look at the function that we're looking at here is that a function for power. I'm going to put this in brackets, I guess. I max squared times r cosine squared omega t and dt. Okay, so we need to take this integral. So I'm going to do in pretty quick order here. So what comes out in front, let's see here. Let me take out my I max squared r, and everything else I'm going to leave in there. So I have the 1 over t. It says t minus 0, but I'm just going to put 1 over t. Integral from 0 to t cosine squared omega t dt. Okay, so my I max and my resistance, those are constant. The max value for I doesn't change. I changes, but the maximum value for I it doesn't change. And R, my resistance doesn't change. So I take that outside the integral, and I'm left with this. We don't have time to kind of unfold this, but let me give you a hint how I do this integral. We can make a substitution here using trig of 1/2 1 plus cosine 2 omega t, I think, 2 theta. Okay, so we're going to make that substitution for cosine squared omega t. I think, what's that called? I don't think it's double angle formula, but I can't remember the name of it. But I know that's one of the trig identities that we use. So we're doing a half angle. Might be half angle. Yeah, I really don't remember these names. Okay, we'll go with half angle. No, I don't think it's power reducing, but I think it's half angle. Karen seemed so positive with the response there. So I'll take it to be half angle. Okay, So we're using this half angle formula there to plug it in. And what's going to happen when you integrate over the period there, cosine 2 omega t essentially goes to 0. And what you're left with, this whole thing just becomes 1/2. So we're left with this. So P average, oh, let me do it in black here. Oh, it might be. It might be. I really don't remember the name of it. Oh, okay. Thanks. Power reducing. All right, so this is what we get. P average equals I max squared R times 1/2. All right, but I could rewrite this another way. I could rewrite it like this. All right, isn't that the same thing algebraically? Okay, so what we're going to do with this here, right here, I max over square root 2. I'm going to call this a different I. Because if you kind of look at this overall function, it almost looks like what we started out with, right? I squared over R, but that I squared is kind of a little different, right? It's a I max over root 2. All right, so we're going to, this is actually called the root mean square. Okay, so let me make that substitution here. And I'll tell you why in a second. Okay, so we made a substitution here. And let me say what I just did up here on the top. IRMS is related to the maximum value I max over root 2. Okay, now where does the root mean square come from? It's kind of like what we just did. So root mean square, we took I squared, right? We did I squared. That's what we did over here. Right here, we squared it and we squared this function. So I squared, and then once we took I squared, we took the average of it. All right, but remember that's I squared, that's amp squared. So to get back current, so we squared I, we took the average of that function, right? That's what we did right here. We took the average of I. This is taking average. Or I guess this is taking the average of I right here. So we took the average of I, and then to get back our current, we had to take the square root. Okay, so that's called the root mean square. And so we get back our original equation for power with one caveat, right? One note that we're not looking at the instantaneous current, right? Instantaneous current is changing. It's not constant, right? It follows that cosine function. But this IRMS is related to the average, not quite the same thing as average, but it's related to the average. And so the reason why we do that, one, is because if you're going to use an ammeter to measure current, that current will constantly be fluctuating from positive value to a negative value, and so it wouldn't really be helpful, right? And if you took the average of your current function, like the one we had over here, if we took the average of this, right, over a certain period of time, over a longer period of time, you should eventually get 0. Okay, so we don't want to take the average of that. But the reason why this is helpful is because if you measure if you use an ammeter, the ammeter tells you this value, even though current is changing at a pretty rapid rate, right? I think the frequency that we use here in the United States is 60 hertz. So current is changing pretty rapidly, but the ammeter will just tell you this number. It also tells you, you're also able to compare it with a DC circuit. So if you have a DC circuit with this amount of current, it will deliver the same amount of power. Okay, So we're going to be talking about IRMS quite a bit here. So let me box that answer, or that equation. And if we're talking about IRMS, we could also just multiply both sides by resistance. We could get VRMS. So you really have to be careful when you're looking at examples, or when you start doing problems in chapter 32, whether you're given a maximum value or an RMS value. Because depending on what you're given, you might have to use these two equations that I boxed to switch from one sort of value to your other. So if the problem asks for maximum value, you have to make sure you're plugging in maximum voltage, maximum current. If the problem asks for your RMS value, you have to make sure you're plugging into your Ohm's law, RMS and current and RMS voltage. Okay. All right, so we're gonna stop there with chapter 32. Just want to touch on it a little bit. When we come back in our next lecture, we're going to be looking at what happens if you put a capacitor and an inductor in your AC circuit. Okay, so we'll talk about that next time.